Hi everyone, I'm going to take you through an example here in the log and exponential 2 series. This is the example from page 18 of the handout. It's on Newton's law of cooling, which is a special differential equation. And Newton's law of cooling says that the rate of change of an object is proportional to the difference between the temperature of that object and its surrounding temperature. You can see the first line in this question that I'm going to go through describes that exact situation. So when you think about this, it makes sense. If you've got a cup of coffee at 100 degrees, boiling water, and you put it in a freezer that's at 0 degrees, or a fridge that's at 0 degrees, it's cooling down really quickly at the start. The difference between those two temperatures is a lot, and so it's cooling down quickly. However, when the cup of coffee gets down to 5 degrees, because it's only 5 degrees difference from the surrounding temperature, it's cooling a lot slower. This is Newton's differential equation to describe that situation. So I'm going to apply it to some forensics here. This is how we work out the time of death. So we've got a team at CSI that we discovered a dead body at 4 p.m. in a shallow stream. The man's body temperature at that time is 15 degrees. And the water temperature is 6 degrees. Measured an hour later, the man's body temperature has dropped to 8 degrees. We want to know when was the time of death. And the man's normal body temperature is 37 degrees. So let's go through the general solution and then apply all these numbers here. So we've gone through this first bit here. I've just changed the proportionality sign to an equal sign by adding in this k here. Now that makes it an equation. This value of k will just help us with how fast a body is cooling down. So let's put in what we know. T0 here is the outside or the surrounding temperature. Now that's 6 degrees. Now you may say the water temperature may have changed, but let's assume that it's constant throughout that time. So that is equal to 6. So I'm going to solve this differential equation now. We have to separate the variables, so we take the t minus 6 over to this side, put the dt over this side and integrate. On the left hand side, this is going to be ln, so ln t minus 6. On the right hand side, the integral of k with respect to t is kt plus c. Okay, what do we know? We know that when we found the body, and I'm saying 4 p.m. is t equals 0, we know the temperature of the body was 15, so I'm going to substitute that in now. T equals 0, little t equals 0 that is, and big T, the temperature, equals 15. That gives us ln 9 is equal to c. So now we know the value of that constant of integration there on the end. Now what do we need to find? We need to find k. Well, we've got some more information. We know that 1 hour later, the body's temperature was 8 degrees. So I'm going to put that in. Little t equals 1 hour later, and big T is equal to 8 right here. Alright, so solving that, we get ln 2 is k plus ln 9. So k is ln 2 minus ln 9, or ln 2 over 9. Now we've got the whole equation here at the bottom. Okay, so this describes the relationship between T, the temperature of the body, and little t, which is time in hours. So a bit confusing with the t's here. Okay, so we want to know what is going on. So let's solve this differential equation now. So we want to get t on its own. We've got ln here. So I'm going to go e to the power of both sides. The e and the ln cancel on the left-hand side. And it's e to the power of that whole thing there. So just be careful, as I've highlighted, that multiplication sign there, you get that right. Now I've left this in exact form because it's going to work out a little bit, it's going to work out nicely here. So on the left-hand side, t minus 6, e to the power of ln 9 is just 9, e to the power of ln 2/9 t. Let's leave that... well, let's change that. E to the power of ln 2/9 t. Look over here in the red. That's the same as e to the ln 2/9 to the power of t. E to the power of ln 2/9 obviously cancels out, and we just get 2/9 to the power of t. So my equation right there, where I've got the asterisk, or you could just change this bit here for 2/9 to the power of t. Now it's just, once I've got this expression here, it's just a matter of finding what's the value of little t, what was the time when the body temperature was 37. So substituting 37 into there, subtract 6, divide by 9, gets us to this stage. Now, how do we go from here? Got 2 ninths power of t equals that. Once again, we're going to need logarithms. So natural log of both sides, the t comes down the front, divide by ln 2 ninths, we get negative 0.8223 hours. Now if you convert that decimal into minutes and seconds, you get 49 minutes 20 seconds. Now the negative just means that it was before 4 p.m. So we're talking about 49 minutes 20 seconds before 4 p.m., which is 3:11 p.m. Now these things are really important. Real life case, I know in New Zealand, the time of death was so critical in terms of convicting the person who had an alibi up to a certain time. And you know, in this case here, we know that it's not exact. In this case here, there's a few variations. You know, the body temperature might not be exactly 37. The stream may have changed temperature, but it's a really good estimate that around about 3:10 p.m. is when that body started cooling down. So that's the way that you can apply Newton's law of cooling to a problem like this.